Welcome back to Chapter 5. We're on Part 2, and today we are talking all about standard deviation. So sit back, relax, and be prepared to learn about one of the most important concepts in this class that we will definitely be talking about all semester. Standard deviation is the most common measure of variability when you are calculating the mean. So when you have data that lends itself to calculating mean as your measure of central tendency, you're going to also calculate standard deviation as your measure of variability. And conceptually, what standard deviation is an average difference of every single score in the distribution from the mean. So if you're thinking, okay, well, on average, how far apart are these scores from the mean? That is what the standard deviation is trying to get at. And the whole point of why we're doing this, right? Like, why are we calculating standard deviations? On the one hand, we're trying to summarize a distribution. We're trying to summarize data. So if you give somebody the mean and standard deviation for a particular distribution, they have a decent idea of what the data is going to look like. How much variation is there? Is it tightly packed around the mean? What is the mean? But there's another important concept here that we're trying to figure out an average distance that all the raw scores are away from the mean, and then we can compare, let's say, a single participant's raw score against that average, that standard deviation, and we can say, well, how weird is this participant's score? Are they like way different from most other participants, or are they pretty similar? So we'll have some basis for comparison. But a funny thing would happen if you tried to actually calculate the average distance that each score in a distribution was away from the mean. All of the numbers would cancel each other out, and you would end up with an average distance from the mean of 0, which is impossible. Like unless every single value is exactly the same, which means, if you had uh, a bunch of scores that were all 6 and you tried to find the mean of that, it would be 6. Then there's no variation. But that's not how most things work. And so I'll try to prove this to you a little bit. Let's say you just have 3 scores in an entire distribution, just 3. The scores are 3, 4, and 5. Those are the scores. The mean of 3, 4, and 5 is 4. And then if you try to average the difference that each of those scores is away from the mean, you would take 3 minus 4, which gives you -1, 4 minus 4, which gives you 0, and 5 minus 4, which gives you 1. Then you would try to average those numbers together. Adding -1 and 0 and 1 gives you 0. And if you try to average those by dividing them by the number of scores, which there's 3 of, 0 divided by 3 is 0. So again, you can't do it because trying to calculate an average distance away from the mean just results in all those numbers canceling out and giving you 0 variance or variability, which is impossible, almost impossible. So instead, what we do is we don't just try to calculate the average distance that scores are apart. We get around this idea that they'll all cancel each other out by squaring all of the difference scores. And so instead of -1 on the previous example, we would have -1 times -1, which is +1, and then everything becomes a positive number, and you can add them together and find the averages. And so let's actually walk through how we would actually calculate the standard deviation. And if you read the last slide, word for word, it's talking about sums of squares and variance and all this stuff. And yeah, very confusing stuff. So that's why we'll break it down and we'll walk through it together. So there's 4 basic steps. The first step is you're going to find the difference score for each score in the distribution. So you're going to actually just subtract the mean from every single score in a distribution. You can imagine that doing this by hand, if you have 200 participant scores, you'd have to make 200 different scores. So it can be a lot of work by hand. The second step is you're going to find what we call the sum of squares. And so you're first going to square all of those different scores you calculated in step 1 And then you're going to add all of those values together. Third, you're going to find what is called the variance, where you divide that sum of squares from step 2 by the number of scores. And then finally, you convert variance to standard deviation by taking the square root of the variance. All right, let's say we've got a distribution of exam scores from students in a class, right? So it's like 55 and 60, 65, all the way up to 95. If you were to take the mean, the average of this group of data, this distribution, you'd get 75. And so in order to start calculating the standard deviation, what we would first have to do is calculate what's called a difference score. And the difference score is simply each raw score minus the mean. And in the language of mathematics, that would just be x, which is the raw score, minus x bar, which is the mean, right? So what you do is you take every single participant's raw score, their exam score, and you're going to subtract it from the average exam score. You do that for all of the participants. So you can see at the bottom, the person who scored a 55, well, you subtract the mean from that, and that gives you minus 20. And what that minus 20 is, that difference score, is simply the distance that that person's raw score is away from the mean. It's 20 points below the mean, right? And that makes sense. This person scored a 55, which is pretty low, and so they scored pretty well below the mean. What happens if you score exactly at the mean? There are a couple people who have scores of 75. Well, 75 minus 75 is 0, so they're 0 distance away from the mean because that is the mean, right? So this initial stage is just saying, oh, for each participant, how far away are they from the mean? Now what we'd really like to do is just take an average of all those different scores, and that would tell us, well, the average distance that students are from the mean when it comes to exam scores in this sample. But the problem is, again, if you just add up all of these different scores, they're going to equal 0. They're going to cancel each other out. And so you can't actually figure out a straight up average distance that each of these students is away from the mean. Instead, we're going to have to do a little bit of math magic. Next, we're going to square all of the different scores that we calculated in the previous step. So you can see that, for instance, the difference score of negative 20, we're going to square that. Negative 20 times negative 20 is 400. And you just do that for every single difference score that you already calculated. Then you add all of those squared difference scores, you add them together. And the add all scores together symbol is this Greek letter sigma, which looks like an uppercase E. And so finally, doing this part of adding all of those squared difference scores together gives us what we call the sum of squares. Okay, we're getting closer. So the third step is to find what's called the variance. The variance, very unfortunately, is denoted by this little kind of O with the curly Q thing on it. That is also called sigma. That's, unfortunately, in the Greek alphabet, this is a lowercase sigma, whereas the symbol for sum of is uppercase sigma. I didn't make this up, so I apologize. It's a little unnecessarily confusing. So what we're trying to do is find what's called the variance, which is lowercase sigma squared. Lowercase sigma squared, that's variance. And how you find that is it is equal to the sums of squares, SS, from the previous slide, divided by the entire population, the population size. Okay, so this is how you're going to find variance for a population. Breaking that down even further to the right, the sum of squares is the sum, capital sigma, of the squared difference scores for each participant, all of that divided by the population size, right? And so if you were to actually calculate this using all the numbers on the previous slides, the variance, sigma squared, equals 1,550 divided by 12. There are 12 people
or in that particular population, there's 12 scores. And then that gives you a final variance of 129.17. Now here's the thing about variance. Variance is itself a measure of variability. It's actually kind of what we've been looking for, right? We've been trying to say, well, what's the average distance that each of the scores is away from the mean? And you can see the sums of squares divided by the number of scores. That's taking a mean, that's an average. So we're done, right? No, we're not done, unfortunately, because since we had to square all those different scores, the units of variance are also squared. And so what this 129.17 is saying is that is the amount of points away from the mean on an exam squared. That is points squared away from the mean, which is like, what does that even mean? It's like if you take a bunch of people and you give them a reaction time test where they try to click a button as fast as possible after seeing some flashing light, and then you try to calculate the variance of that, it's going to be in seconds squared. And it's like, what does that mean? I don't even know what seconds squared mean as a conceptual unit, right? So what we have to do is take this number, and finally we will take the square root of it to get it back to normal units, and that will be the standard deviation.
And the way we do that is to take the square root of the variance, and that gives you the standard deviation, which is denoted by the lowercase letter sigma. So finally, the standard deviation from all of those calculations that we just did is 11.37. And that is basically, conceptually, the average distance apart from the mean that all the scores in the distribution are. So the higher the standard deviation, the further apart scores tend to be from the mean. The lower the standard deviation, the more grouped up and bunched up the scores will be right around the mean.
So thinking about this conceptually, right? The mean exam score was 75. The standard deviation is 11.37. So what that means is that a lot of students scored within basically 11.5 points of the mean. So a lot of students scored between, what would that be? 75 plus 11 is 86. So a lot of students got between an 86, and then on the other hand, if you take 75 and subtract 11.5 or whatever, that's going to be 64-ish. So between a 64 and an 86, a lot of students kind of scored within that range. If the standard deviation was a lot higher than 11, that means that there's a lot more spread in the scores that students are getting. So maybe some students did really bad. They got like 20 out of 100 or something. And then a decent amount of students got up in the 90s, upper 90s, right? And so then if you find an average that's 75, but you have standard deviation of like 20 points, that means that there's a lot more spread in the scores versus maybe even a much smaller standard deviation, a standard deviation of like 3 points. That means that almost all the students are scoring very, very, very similarly to each other, and it would be more tightly packed around the mean. Quick review question. The sum of all the different scores is always what? The sum of all the different scores away from the mean is always going to be 0 because they will all cancel each other out. Positive scores above the mean and negative scores below the mean will always add up to equal 0.
Now there's a little twist we got to talk about, which is what this last learning objective is about. So why does the standard deviation calculation differ for samples as compared to populations? So the equation we've been talking about this whole time that calculates standard deviation is specific to the population standard deviation. So usually we use Greek symbols when we're talking about population, like we talked about population mean is denoted by the letter mu, which is kind of that U with like a a little teardrop on the end. Here too we have Greek symbol lowercase sigma denoting the population standard deviation. The thing is that this particular equation, number one, you'll never know probably what the standard deviation of the population is because we take samples of populations. We can't access everyone in a population. Another thing is that people have run like many computer models and really advanced statistics to show that actually if you use this particular equation to find standard deviation, it's an underestimate typically of what the true population standard deviation is. And so we'll see how to correct for this on the next slide.
So since that previous equation tends to underestimate the true population standard deviation, we apply a little correction. And you can see in the denominator, now we're talking about lowercase n because this is now the standard deviation for a sample. And you can see that we're using the symbol S as standard deviation of the sample instead of sigma, which would be the standard deviation for a population, right? So in this case, we're applying this little correction, which is n minus 1 to the denominator. What that is functionally doing is it makes the denominator smaller, which makes the overall standard deviation a little bit bigger. And remember, that's because it's a little fix because we were underestimating the standard deviation. Now we want to get a corrected, more on target estimation of the standard deviation. So all that to say is this is the final calculation for standard deviation of a sample. And you will absolutely want to know this, know all the parts of it, know how to calculate it, know how to do it by hand for quizzes and exams. And again, we moved from sigma, which is a population parameter, down to S, which is a sample statistic.
And just to show these side by side for comparison, you can see the population standard deviation has the sigma, and also is the denominator is just the capital N for the entire population size versus standard deviation from a sample, which is denoted by S, and the denominator is now the sample size minus 1. Also, it might help you if you're trying to calculate the standard deviation by hand for a sample. You can use kind of a table like this, or just set up one on a piece of notebook paper or whatever, where you write out each score in the distribution, then you write out the mean in the next column, you subtract the mean from each of those scores, that's the difference score column, and then finally you square all of those difference scores to find the sum of squares. Then at the bottom, you can total the sum of squares, right? You add that all up, and then you have to perform just two little more calculations. Since that total sums of squares needs to be divided by n minus 1 to find the variance, which is denoted by s squared, and then you can square root all of that to actually get finally to the sample standard deviation, which is denoted by S. So hopefully this helps. If you ever are in a space where you need to hand calculate standard deviations for a relatively small set of numbers, this is how I would do it. This is also a good time to bring up the concept of degrees of freedom, which is the number of scores that can vary in a calculation of a statistic. And by that statistic, I mean things like t-scores, f-scores, which we'll get to when we talk about hypothesis testing, or in this case, we can talk about degrees of freedom related to standard deviation. So it's a hard concept to kind of explain, but I'll try my best. So basically, if you have a set of data, any distribution of data, let's say it's the average height, the height of a sample of students or something, and if you already know the sample mean height, the average height of all the people in that sample, if you start displaying one by one the individual heights of all the people in that sample, by the time you get to the last score, the last height, you already know what that one's going to be because it has to combine to create the mean, which you already know about. And so another example of this might be if you got a small bookshelf and there's only 6 books on that shelf, and you figure out the total width of all 6 books is, let's say, 15 inches. And you take the first one off of the shelf and it measures 2 inches in width. Okay, that means the next 5 books have to add up to 13 inches, right? Then you take the second book off the shelf, and that one is also 2 inches, and that's cool. Okay, that means the next 4 books have to add up to 11 inches. And if you keep on doing that process and that process until you're left with the last book, you already know what the width of that book is without even measuring it, because it has to add up with the other books to a total of 15 inches. So that's kind of how this works. So when we're calculating standard deviation, because we already know what the mean is and we've got all of the sample scores, we also can think of this denominator factor as the degrees of freedom, which is n minus 1, meaning all of those scores are free to vary except for the very last one. That's why we subtract that 1 out of it. And hopefully this will make some more sense when we talk about calculating other statistics like correlations, which have an n minus 2 degrees of freedom, and you'll see why that is later on. All right, and so wrapping up, this is really important. When you have a set of data and you have a lot of different kinds of variables, different scales of measurements, which we've been talking about, like nominal and ordinal and that kind of stuff, how do you know which measure of variability to use depending on what variable you want to explain? So which measure of variability you decide on depends very heavily on the scale of measurement each of your variables are. So for nominal variables, which again are just categories like eye color or religion or gender or any of that stuff, you can't calculate measures of variability. All you're doing is counting people in different categories, right? So there isn't actually an appropriate measure of variability there. It's just counts and frequencies and percentages. For ordinal, interval, and ratio variables, though, if you calculated the mean, which we mostly do on interval and ratio variables, then you should use the standard deviation. So the mean and standard deviation go together. But if you calculated the median or the mode, maybe you have skewed data, maybe you have ordinal data, then you want to use either range or interquartile range. And remember, interquartile range is generally preferable because the range, just plain old range, is really affected by extreme scores, and so people don't use it that often. And if you're ever in doubt, here's a really nice flow chart that shows you which measure of variability to use based on your data. Okay, so if you use the mean as your measure of central tendency, which measure of variability should you use? Well, that's going to be the standard deviation. Okay, so anytime you see mean, you should think, oh, I'm going to also report the standard deviation. If you use median, then most of the time people are going to use interquartile range. And if you have nominal data, you don't got nothing. You can report the mode, and then there is no measure of variability that you would report for that. All right, we did it. Another chapter in the books. I know this one's a little bit longer, so thanks for sticking with me to the end, and enjoy this cute puppy meme.